Hello, and welcome to NHP's live webinar on improved business continuity with power quality. My name is Stephanie O'Donnell. I'm the product engineer for integrated power and energy for NHP Electrical Engineering. With me are some special guests.
Daniel Barnes, and I am the business development representative for the industrial products business within New South Wales.
And I'm George Janiszewski. I'm an application engineer based in Auckland, New Zealand.
If you have any questions throughout the webinar, please use the Q&A section located on your webinar screen to submit them, and we'll be happy to address those at the conclusion of the webinar. This is just one in a series of webinars created to showcase NHP smart devices powered by smart distribution and embedding smart safety into operational processes, providing our customers with better visibility into processes, data, and analytics. So the goal for today's webinar is to cover the following key points: the importance of good power quality, the Delta SVG and APF technology explained, and we'll also showcase a few key examples of this range in action. So first up, what's the deal with power quality? So plenty of you out there have probably already seen the beer glass analogy. So we're not going to do that again, but instead we'll just do a quick overview of what power quality is. So first off, high power quality is the ability to deliver a clean and stable power supply. Essentially, this is a pure, noise-free sinusoidal wave with voltage and current in phase, free of any disruptions. There are three main power quality issues commonly faced. First is power factor. A poor power factor results in a phase angle difference between the current and voltage waveforms of an AC system. Second is harmonics, which is multiples of the fundamental frequency of 50 Hz impacting the supply, resulting in heavily distorted waveforms. Finally, we have network imbalance, which is differing line voltages across phases caused by unbalanced loads and single phase and phase-to-phase connections. So first, let's talk about power factor. So poor power factor results in poor electrical efficiency. So this can result in larger generation capacity requirements, larger size transmission lines and cables, larger transformers and other distribution devices, and as a result, it means higher capital expenditure and operating costs. So this is also why energy providers are now passing on penalties to large consumers of reactive energy. So here's an example that we see of power bills now changing and increasing because suppliers are now charging for reactive energy. So Sharp sawmills, so massive change in their power bills. Their retailer has recently changed their supply tariff. So as a sawmill, their machines, their motors are generally only running at about 20% duty cycle and only operating at full capacity when the loads are passing through them. So if they're not operating all the time, you'd think that they wouldn't be so expensive. However, while energy consumption is low, reactive power is quite high. And as a result, on-site power factor is fairly low at 0.57. So they want to reduce their bills? Well, Mr. Sharp should consider implementing some power factor correction on site. We'll go into how he can achieve that shortly, but first, let's talk about harmonics. So, harmonics, as I said before, is the heavily distorted waveform that impact on supply. So common causes of this are VSDs, LED lighting, and switch mode power supplies. So it can cause a variety of issues, including overheating of standard electrical supply, conductor losses, poor power factor, harmonic resonance, large load currents seen through neutral wires of three-phase systems. It also affects a lot of sensitive equipment, including computers, motor drives, telecommunication systems, and a lot of control and timing wires will experience some interference as well. It can also cause nuisance tripping and voltage distortion on neighbouring power supplies. So for businesses, this means increased maintenance and equipment replacement costs, costly interruptions and downtimes, and also non-compliance to service and installation requirements. While the limits may vary from country to country and state to state, there are standards for maximum satisfactory harmonic levels on site. So here's an example of a site that has harmonics present. So they upgraded a number of pumps on site and installed a couple of large VSDs. At the time, there was no effective harmonic filtering available on site, and as a result, not long after the VSDs were powered up, started seeing some visible signs of the transformer overheating. So power quality analysis was done for the site, and a high amount of current distortion was measured. So best result was to get an active harmonic filter in there. So let's just quickly summarize benefits of good power quality. So first off is your lower apparent power draw can significantly reduce your energy bills and reduce demand on supporting infrastructure. It's also less financial penalties. As I showed before, we're now getting tariffs, or utility providers are providing additional tariffs and additional penalties now for low power factor. So having good power quality will reduce that. It also helps optimize power infrastructure. So we're utilizing power more effectively and efficiently. And finally, it's lowering carbon emissions as we're reducing overall power draw and inherent losses. So therefore, we're reducing carbon output. So now that we've gone over power quality, let's look at the types of technologies that NHP can provide to give you good site power quality. So there are many different technologies available today for power quality, but here's just a few shown here. Today though, we'll be focusing on static VAR generators and active power filters. For an in-depth look at how the low voltage power quality products compare with one another, please visit our YouTube channel. We have a great video from our colleague Shane Townsend that goes through the low voltage power quality products. First up, we have static VAR generators, also known as SVGs. So these are based on inverter technology to respond dynamically to changing power factor requirements. They can correct both lagging and leading power factor. They have a very quick response time, long service life, reduced possibility of resonance, and not impacted by site harmonics. So in general, in terms of applications, these are best suited for low voltage networks where the load is not constant and predictable. So places like the sawmill example from before, welding equipment, injection molding, and commercial buildings. So let's dive into the technology of static VAR generators a bit more. So they have some pretty good advantages over capacitor bank PFC. So they can correct to a power factor of 0.99 and above for both lagging and leading. They also provide dynamic stepless correction, and it's that quick response time of less than 20 milliseconds that really makes them stand out over capacitors. A lot of the time it can be minutes for a capacitor bank to get back to reacting to changes. They're also immune to site harmonics, and there are 4-wire models available that will work with non-balanced networks. Also, given the lack of moving components, the maintenance requirements are quite low, so service life is quite long. Some considerations though to make with static VAR generators: they do have a higher initial investment relative to contactor-based PFC, but we'll talk about that a little bit later. They also do have greater heat dissipation, but they also have additional venting and that to compensate for that. And static VAR generators, they're purely there for reactive power, so they do not have harmonic mitigation. But for harmonic mitigation, that's why we have active harmonic filters. So they can correct both power factor and harmonics. The way that they work is that they inject adaptive current that matches the harmonic magnitude, but at the opposite phase angle, restoring the waveform to a smooth sine wave. So by mitigating harmonics, the APF is improving the distortion power factor on site. APF systems can also correct for leading or lagging displacement power factor, same as SVG. So, same results as before, or same advantages as before. The quick response time of less than 20 milliseconds to any changes in the waveform. They provide harmonic mitigation of up to the 50th harmonic. They can provide load balancing capabilities. And in particular, the 4-wire models work with non-balanced networks and compensate for that. And again, not a whole lot of moving parts, therefore low maintenance requirements. Your considerations, again, is that higher initial investment due to additional functionalities. I'm going to talk about that a little bit more now. So while up front, the price of an SVG or an APF is higher than traditional methods of power factor correction, it does have reduced total cost of ownership. So not only does it improve power factor and reduce harmonics more effectively than traditional methods, it has less maintenance, longer service life of components. So your service and maintenance is quick and easy. You don't have to constantly check capacitor levels and replace them over the years. These systems are also modular, with easy to expand on their capacity, so for future expansion. So let's talk about the superior technology of SVG and APF compared to other power quality methods. So it's that modular design again that I mentioned before that allows you to make hybrid systems so you can have SVG and APF modules in a single cabinet and effectively providing all levels of power quality. So under any load conditions, you're maintaining your power factor and your harmonic levels. Again, it corrects both lagging or leading power factor and does load balancing. It's that fast response time. And it can correct both odd and even harmonics, specifically for the APF. Okay, so Delta APF and SVG, they're designed for the future. So you have peace of mind in the long term. So that modular design that I keep bringing up, it allows for expandability and future expansion. So the Delta SVG and APF cabinets have the largest output in a single tier in the market. So that's 700 kVAR and 700 amp in one cabinet. So you don't have to buy all of that at once. You can buy only a couple of modules and be ready for future expansion. Also available, they have comms on there, so remote monitoring is available as a standard option. So finally, let's talk about Delta SVG and APF products in the wild. So firstly, I'll talk about the installation that we have at our National Manufacturing and Distribution Centre in Laverton, Victoria. So the distribution centre is 12,000 square metres and it develops world-class customised solutions through manufacturing, assembly, servicing, design, engineering and distribution of over 1,500 stock lines. So the facility itself had a power factor of 0.8 lagging on average, and we required an innovative solution to correct power factor, improve the power utilization on site, and greatly reduce our electricity bills. So given the continuously changing load requirements on our site, a solution was required that would respond dynamically to a wide range of power factor issues. So for us, the Delta SVG was the perfect option. So we've put in a 200 kVAR model. So the SVG itself has minimal maintenance requirements, and the modular nature of the unit made installation easy, and the capacity can be expanded in the future as we require it. So here's some snapshots from our energy monitoring platform that we use at Laverton. As you can see here, the SVG was switched on at around 3:30 p.m. And from that moment onwards, power factor has remained at 0.99, regardless of the load conditions on site. So next, I'll invite Daniel to tell us a little bit about this SVG application at a meat processing plant. So Daniel, can you tell us a bit about this site?
Yeah, thanks, Stephanie. Yeah, so this case study, is one of our leading advertisers out in Western New South Wales. Now, initially, I was engaged I was actually out there assisting the customer scoping a service regime or shutdown for their LV circuit breakers and cat-based correction systems that are existing on their site. Out of that, once the servicing was completed, it actually highlighted multiple issues across their cat-based systems and their circuit breakers as well. But with their cat-based systems, there was a common trend of faulty, depleted or undersized units that were identified. Now, from that point, before we even went down a route of looking at repairs to even salvage what they had existing, as a baseline, we opted to conduct power quality audits throughout all the various main switchboard locations on their site. The reason being their load profiles have changed dramatically over the years. The plant's been in production and it's obviously expanded a lot since then. So those studies allowed us the clarity we needed to size exactly what systems they required and look at the existing cat-based systems and see if they were even feasible or adequate to cope with their current system. After that, at that point, we had a clear vision of what sizes were required. Then it was a case of looking and discussing the customer about what problems they had in the past. Now, from the feedback we got from the customers and what we found during the audit and the servicing was they had a very poor history of component failures across items like contactors, and they experienced a lot of premature depletion on their existing cat-based systems due not only to heat, harmonics, and lack of maintenance. So then we discussed the SVG technology, which plays exactly to address those problems they had experienced with no mechanical moving components such as the contactors, the lack of or non-existent capacitors in the SVG technology, so they've moved away from having that consumable issue and that a big overhead cost. And then also with the dynamic response time with the SVG technology, the efficiency gains that they were able to get with that dynamic response time was an added benefit. Now, they were really welcoming to that technology. Outside of that, what their maintenance crew needed from us was also how they could justify the costs of these systems. So what we did there, we looked at scoping what was going to be the cost to even attempt to repair their existing systems, and there was a large cost associated with that. And then we actually took their utility bills where they were actually falling short even with the current cat-based system and looked at what would be the cost or payback period if they were to invest and move towards that SVG technology. Now, those payback periods, depending on location and rating, did vary. But at the end of the day, you were looking at anywhere from about 2.5 years up to, say, about 3.5 years payback, which they were quite happy with, and when they looked at the cost of what it was also even to attempt to get their existing systems up to where they needed to be, the SVG was the clear winner in that scenario. Now, itself, as far as how it was delivered, a local board builder provided the end user any modifications to accommodate larger breaker ratings, or even a breaker that may have not existed. If some areas didn't have a cap-based system, to do those mods. The end user, their site sparkies, did the actual physical cable install or any CT installation that had to be done, and then NHP provided the assembly of the SVGs and the commissioning support to close off that project. And yeah, they were very happy, and it was a great win for them.
Excellent, excellent. So it's that total cost of ownership, taking that into account rather than just looking at the upfront cost, but
Most
then also everything else with the maintenance requirements, and also they received the 12 months warranty additional.
Yeah, so with the failures they had, any extra warranty that they could have at no charge was really icing on the cake for them, and just an added bonus, which played right into their hands. So that was fantastic.
Of course, of course. Excellent. All right, excellent. So now I'm going to pass over to George. He's going to talk to us about a crusher plant that we have over in New Zealand, where we've got one of these Delta APFs. So, George, tell me a bit about the site and what sort of prompted the customer to look at upgrading their power quality.
Okay, yeah, well, thanks, Stephanie. Well, the site is what's called a grey wacky stone aggregate quarry located near Auckland, New Zealand, and they're supplying around 2 million tonnes of product per year to the Auckland region. And they have existing capability of producing and supplying up to 5 million tonnes per year to contribute to Auckland's growing urbanisation and infrastructural needs. The quarry range of high quality products, including concrete and asphalt aggregates, ceiling chip, and constructional aggregates. Now, the site is located around 12 kilometres from the nearest electrical supply infrastructure, and it's connected by a long piece of wet string, so to speak. That is to say, the 11 kV feeder line has a very low capacity, and it's not particularly reliable either. So the quarry owners applied to the local power authority to expand the capacity of the feeder line, and they were quoted something in the order of $4 million to do the upgrade. Well, yes, it was, and the quarry owners decided to take responsibility for their own destiny, and instead, at much lower cost, installed 4 500 kVA diesel generator sets, giving a total of 2 MVA of generator capacity on site, in addition to the existing 11 kV line, which feeds a single 750 kVA transformer. So normally, the plant runs with the two supplies separated. That is, the 750 kVA transformer feeds the vital main rock crushing plant, and the generators supply the remainder of the plant. However, during an outage of the 11 kV feeder, which apparently happens fairly often, they have the ability to run the entire plant from generator power. So we were first approached by the quarry to look at improving the very poor power factor on the generator-fed portion of the plant. At the time, there was a lot of concern around the use of power factor correction in the context of the generators, fear about going into leading power factor and so on. However, a very carefully engineered 400 kVAR capacitor-based PFC system was installed and commissioned by NHP, and this immediately reduced their apparent power draw to the point where they could completely switch off one of the generators, with associated costs of fuel and maintenance. So, yeah.
Excellent. So what prompted them, though, to look at using an APF?
Well, more recently, the quarry management decided to enhance their product quality by changing the main rock crusher from fixed speed to variable speed control. The main shaft of the crusher was originally driven by a pair of 355 kilowatt induction motors, one being started on an NHP supplied soft starter, and the second motor being brought on direct online once the rotor was up to speed. And this was all fine because, it was relatively low harmonics. But when the new variable speed drive system, or VSD system, was supplied by NHP, the new system allows one motor to act as a speed master, and the second motor operates as a torque slave, thereby equally sharing the rock crusher load. However, the consequence of almost fully loading the 750 kVA transformer with VSD load meant that the harmonic voltage distortion levels on the 415 volt bus were in the order of 11 to 12%, which is far in excess of the usually accepted 5% maximum.
Yes, of course.
So NHP supplied and commissioned a Delta active power filter, or APF, and this had the effect of reducing the total harmonic voltage distortion from that 11-12% down to under 5%, typically 4 to 4.5%, with the rock crusher running at full load. Now, one of the key considerations in the application of the APF was this low reliability of the 11 kV supply. So should the 11 kV feeder go offline, the entire site needs to run from generator power. So without the APF, the harmonic voltage distortion would have been far, far too great for the existing capacitor-based power factor correction system to tolerate, and would inevitably have suffered damage and gone offline, resulting in the entire plant becoming inoperable altogether.
Mm-hmm.
Yeah.
Definitely don't want that. So.
Indeed.
So in the end, though, it was a great result. And so again, this was commissioned by NHP. Is that correct? So they've
Yes, it was. Yes.
extra 12 months warranty.
There's an image of the customer standing there leaning against the APF with a great smile on his face, showing total satisfaction there.
Excellent. Excellent. Great to hear.
Thanks,
All
Steph.
right. Thank you. So in summary, maintaining good power quality is critical. It allows you to utilize your power more efficiently and effectively, and it can reduce electricity bills and reduce demand on supporting infrastructure. So Delta SVG and APF is the smart investment choice for you. It provides the latest technology in power quality, and it can provide a rapid response for all load requirements. It also has less maintenance involved compared to other technologies and has a longer service life overall. Finally, the modular nature of Delta SVG and APF means that you're set up for any future expansion. Also, NHP is here to help you. So our team has the tools and expertise to provide the right solution for your application. We provide an additional 12 months warranty for free on Delta SVG and APF when we commission it for you, making sure that you get the best result straight away. If you would like to find out more about our Delta Power Quality range, or you have further interest in developing your knowledge on power quality, we have brochures, selection guides, and technical news articles available on our website in the Okay, so now we will answer a couple of questions that you guys have sent through during the presentation. So the first question, Daniel, I'll get you to answer, is how does static VAR generators, like compared to capacitors, like how do they respond to harmonic?
In that case, on the Delta systems, APF or SVG, and the cap-based systems, neither of those systems induce harmonics into the system. But if there is existing harmonic issues on site, Delta systems, SVG and APF are not affected, but will not be affected by those. However, capacitors themselves do have harmonic levels that you must comply to as per the manufacturer's recommendations. And in most systems, you also have additional costs for blocking reactors to deal with the harmonic issues that capacitors can be affected. So, yeah.
Okay, thank you. And a question for you, George. So we've got here, what is the mean time before failure and mean time to repair figures for the Delta SVG and APF?
Yeah, sure, Steph. So mean time before failure is typically quoted around about 100,000 hours. So that's, you know, well in excess of 10 to 12 years type of thing. And the MTTR, the mean time to repair, is quoted as being typically less than 15 minutes, assuming obviously that you have the necessary componentry to hand.
Yep, of course. Thank you. Okay, we've also been asked what kind of thermal losses you can expect with the SVG. So that was mentioned in the presentation. So there is it's 3% of the rated capacity thermal loss. And finally, actually, a few more coming through. Thank you. But George, there's one here. Does the touch interface on the Delta unit support VNC or remote viewing?
VNC as in virtual network computing. No, the screen doesn't actually support VNC, but it has a feature that is equivalent to it. The touch screen has a web server built in, which serves up a web page which effectively mimics the HMI screen, which enables you by remote, either Modbus RTU, Modbus TCP, or if you have a cellular mechanism for connecting to it, enables you to remotely drive the HMI as though you were right in front of the device.
Okay, great. Thank you. And another question has just come through, but that's again asking about the heat generation. So as we just said, 3% of the rating of the. So if there are not any more questions, I guess that's all we've got for today. So thank you everyone for joining us for this webinar. I hope you all found it beneficial, and if you'd like to watch it again, we will be sending a recording through via email that will be uploaded onto the NHP YouTube channel. There was also some questions around the links resource center not working, so we'll be providing those again in that email. So to find any more webinars in this series, simply click the button in the call to action section on your screen, and that will take you to our website and to our YouTube channel. So shortly you'll see a pop-up on your screen of a short survey, and we'd be grateful if you can just take 5 minutes of your time to provide our feedback. If you have any further questions about power quality and our range of products, please contact your local NHP. So again, thanks everyone. Yes, have a great day.